All right, let's look at problem 14.8. In this problem, we have this guy named Olav, and he's riding at 15 miles an hour, starting at t equals 0. They don't really say that, but I think we can assume that at 33 feet away from a street light. The street light's 10 feet above the ground. He rides this way. We want to know how bright the light is on him as he gets closer and closer. And they tell us that the brightness varies as distance squared, which is what it does. All light spread out is distance squared. So the brightness of our light, call it C for candle power, the number of candles equivalent, right? So like 1,000 candles or something, is some number K, which we don't know, divided by the distance you are from the light squared, which makes sense. If you go twice as far away, it should be 4 times dimmer because the light spreads out as distance squared. It gets out bigger as area. That's how most things spread out. Gravity spreads out that way. Sound spread, it gets dimmer that way. That's just the way it works. Okay, so that's our problem. Now in part A, we're supposed to figure out what that K is, right? Because that helps us get the answer. So they tell us that you went out there with the measurement, and they said that when your distance was 20 feet away, their instrument said that it was, the number candle power was what? In part A was 1. You got 1 candle power. That's pretty weak. 1 candle at 20 feet away. It's like a candle of intensity of 1 candle. Well, whatever. Okay, so that's 1. So what is K? Well, C is 1. So we say 1 is equal to K divided by distance squared. D is 20, so 20 squared, which is 400. Multiply both sides by 400, and we get 400 is equal to K. So now we have our formula. C is equal to 400 divided by distance squared. K is 400. Okay, good. Now part B says, find a function which gives the intensity of the light shining on Olav as a function of time in seconds. So now we want a formula for the intensity of light C. We're going to use this formula, but we want to use it on him as time goes on. Okay, now we can guess that time is going to go on. It's going to be brightest when he's right underneath the light, right here. Right, it just makes sense. It's going to be brightest when he's right underneath the light, because that's when he's closest, and it's going to get further away again. But the distance he is from the light's 10 feet in the air, so the distance he is kind of complicated. It's a right triangle kind of thing, right? So here is the distance, right? That's how far he is from the light. So he rides this way, but we have to do that distance thing there. So, we're going to have to do some Pythagorean theorems or something. Okay, now we also know he's riding 15 miles per hour, but everything else is in feet and seconds. So we're going to have to change 15 miles per hour. That's our first step. We're going to change 15 miles per hour to 2 feet per second. So let's do that. So we have 15 miles, and hopefully you guys remember how to do this. You always write it as a fraction because it helps you not make mistakes. And then remember, we want to get rid of the hours, so I put 1 hour is the same thing as 60 times 60, or 3,600 seconds. Now the hours cancel, so you know you did it right. Time, let's see, we want a mile in feet, and I remember that there are 5,280 feet is the same thing as 1 mile. And again, I know I did it right because the miles cancel, and we're left with 5,280 divided by 3,600 times 15. And if you put that on the calculator, you get, let's see, 5,280 divided by 3,600. You get exactly 22. They must have done that on purpose to make our life easy. Because what are the chances, right? So it's 22 feet per second. Nice, pretty number. Okay, that's not the answer for part B. That's just what we got to figure out. All right, now, as he rides this way, right, let's say he gets to right here. Okay, then we want to know his distance. Now his distance looks like this, right? Still a right triangle, but looks like this. So his distance is 33, right? The big number. This big. So okay, well let's say this. So let's say this is his new distance, right? Let's call that x. That's his new distance. It is the starting distance, 33, minus how far he went in that time, which is velocity times time, right? 22 feet per second times the number of seconds. This distance he went is his velocity times time. So how far he is was the full distance minus vt. Okay, so his distance from the light, horizontal, right? That's where he is. His position, we could say, his x position is is going to be the starting position minus his distance he went because he pedaled. Times 0 is 33, so this formula works. Always check that, right? Make sure it works. And so his velocity we just figured out was 22. So does this be 33 minus 22t? That's his x distance. Okay, now we can write what the intensity is. C is k over d squared, which is k is 400. We figured that out. So it's 400 divided by, okay, we have to do some right triangle stuff here. So, and this is d. So d squared is x squared plus 10 squared. Right? So I'll write that over here. So d squared is x squared plus 10 squared, or d squared is x is this. So 33 minus 22t squared plus 100. So we have a d squared here, which is nice. We don't have to have a square root. So we just put in the d squared there. So that's 33 minus 22t squared plus 100. That's how bright the light will be on him as a function of time, which is what they wanted to know. So find the function, right, that's part B. We did it. Hooray. Let's see if we can figure C here before I run out of room. C, when will the light on Olav have maximum intensity? Well, we already know, obviously, it's going to be when he's right underneath the light, so when the distance is 33 feet. But looking in here, they want to know when, right? So looking in here, this is always positive because it's squared. So this will be the brightest when the bottom is the smallest it can be. Since this is always positive because it's squared, this smallest it can be when this is 0. When this is 0, we just have 100, and the brightness will be 4. Right? That'll be the brightest it can be because this can only be positive, and so we want it to be 0 to make the bottom as small as possible. I made that clear? I think I did. Okay, so we want that to be 0. So we want 33 minus 22t equals 0. Put the 22 over here. So 22t is equal to 33, or t is equal to 33 divided by 22, which is, see, 11 goes into both of those. 3 divided by 2. 1.5 seconds. And 1.5 seconds. Now, does that make sense? And 1.5 seconds is going to be right there. 1 second, he'll be 22. In half a second, it'll be half of 22, which is 11, which is 33. So, yeah, makes sense. We could have seen that right away. He'll be right underneath the light in 1.5 seconds. All right, finally, in part D, when will the intensity of the light be 2 candles? So now, part D, we set this formula equal to 2, and we solve for t. Okay, so we say 400 over 33 minus 22t squared plus 100 is equal to 2. And we solve for t here, what t makes that true. I will let you do that on your own. I know that when you finally, you want to get this by itself, and when you take the square root, you go plus or minus. You're going to get a plus or minus, so there's 2 answers. So just be really careful of that. You're going to get 2 answers because when you solve for this squared thing, you get a plus or minus. This basically means it'll be 2 somewhere before he gets to the light and sometime after he gets to the light, right? Because it's 4 right underneath the light. We know that because this is 0. It's 4 underneath the light. So sometime right here it'll be 2, and then after he passes up the light, it'll be 2 again. So that's why it makes sense there's 2 answers. So be careful that when you take the square root, you have to get a plus or minus in there, which gives you the 2 answers. Okay, very good problem. Again, I don't know why it's in this section. This has nothing to do with linear to linear functions. It's a great problem, but it's nothing to do with linear functions, so whatever. Oh well. Okay.